1, 2, 3. We're now going to find the area of the shaded region given that f of x equals x squared. So essentially what we have to do is we have to understand that an integral, just like we learned in a video that Mrs. Casey did, an integral is actually the sum of all of it's basically what happens when we take the limit of all of the rectangles that we do, so an LRAM or an RRAM or whatever. So we're finding all of these. We take the limit as this distance goes to 0. So what we're essentially doing is we're finding the area under the curve. So if we want to find the integral from, for example, in this case, 0 to 2, so if we want to find the integral for the function x squared, dx from 0 to 2, what we then do is we're going to be finding this entire area underneath. So what that's going to look like is we are going to then have, what we have learned now is that if we find an antiderivative of this function, in this case, it's going to be 1/3 x cubed. We can evaluate this from 0 to 2, just like it said in the fundamental theorem of calculus. We can say that we can have 1/3 x cubed. We're going to make that our big f of x. So if this is our f prime of x, we can make this our big f of x. So 1/3 x cubed plus c. But we don't even really need that plus c for this fundamental theorem of calculus. And the reason why is because we're going to be subtracting these two things together. So I have 1/3 times 2 cubed minus 1/3 0 cubed. Even if I had some constant in there. So really quick, just a sidebar, even if I had some constant in there, what would end up happening to the constant is it would go away after I subtracted those two things. So the constants would cancel. So I don't even really need the constant when I'm doing this fundamental theorem of calculus, where I take the integral and I substitute two things in. So if I look at this answer, I will get 8/3 minus 0, which is 8/3. That once again is not the answer to this question. This 8/3 represents the blue shaded area. So because this 8/3 represents the blue shaded area, what I then have to do in order to find the actual shaded area is figure out what the area of the rectangle was. The area of this entire rectangle is 8. So I have 8, and then I subtract the blue shaded area because I'm not counting that in what I actually have. So 8 minus 8/3 is 24/3 minus 8/3, or 16/3. So my answer to this question is 16/3. Okay, so essentially in order to find the area of this shaded region, I have to do 8 minus this integral, and then I would get the answer. Another way that I can do this problem is, instead of trying to find the area of x squared here, what I can do is I can find the area of 4 minus x squared dx, or the integral of 4 minus x squared dx, evaluated from 0 to 2. So what that is essentially doing is that is finding the area between 4 and x squared. So what's happening is I'm having all of these rectangles essentially start at 4 and go down until I get to x squared, and then I take the limit of these rectangles as x goes to infinity, and like that small area goes to infinity. And so what I would end up then getting is the actual area here. So when I take this integral, I take the integral from 0 to 2 of 4 minus x squared. The function 4 minus x squared, if that is my f prime, the integral that would be associated with this, or one antiderivative of this function, ignoring any constants, would be 4x minus 1/3 x cubed. And we're going to evaluate that from 0 to 2. So if I do that, notice that 4 times 2 ends up being 8. That essentially makes the rectangle. So this 4 is basically acting like we're taking the entire rectangle, finding the area of that, and then we're subtracting the area that was blue earlier. So this is another way of doing this problem, and it might not be as easy geometrically to see, but this is something that ends up happening. It's the entire big rectangle, and then we're subtracting that blue part. So we have 8 minus 1/3 times 2 cubed, so 8/3, and then subtracting 0 minus 0. So I end up with 8 minus 8/3 again, which is 16/3. So that's another way to do this problem. Example 2, given f of x is 2x minus x squared on 0 to 3. First of all, we're going to integrate over the interval 0 to 3. So we're going to do the integral from 0 to 3 of 2x minus x squared dx. What that is doing is that is finding some antiderivative and then substituting in 3 and 0, and then that's essentially finding this area. However, it's not technically finding this area, it's finding the some sort of signed area. So essentially anything that's underneath ends up being negative. So we'll talk about that as we get there. So what we're going to do is we're going to take the integral. So an antiderivative of this is x squared minus 1/3 x cubed. We're going to evaluate that from 0 to 3. So I'm going to substitute values in. So I get 9 minus 27 over 3, which is 9. Then I can subtract what happens when I substitute in 0. So 9 minus 9 is 0. So the integral of this from 0 to 3 is 0. That's clearly not the actual area that we have, but it is the integral. So notice that integrals are actually signed areas. So the this would be like a plus something, and this would be a minus something. And what ends up happening is those pluses and minuses actually seem to end up canceling out. So what we're going to do is we're going to find the actual area of the region bounded by the function in the x-axis. And the way that we can do that is by integrating from 0 to 2 of this function, and then subtracting the integral from 2 to 3 of this function. And the reason why we would want to subtract it is, remember that we get signed areas. So anything that's under here, what I want to do is make it negative, so then it ends up flipping essentially. Basically what we're doing is we're taking this area that was down here, and by making it negative, that integral, what I'm kind of doing is trying to make it look something like this, where I'm counting it as positive. Okay, so that's essentially what we're doing. So I take the integral. Remember, the integral, or an antiderivative, was x squared minus 1/3 x cubed. I'm going to evaluate that from 0 to 2, and then I'm going to subtract what happens when I evaluate this from 2 to 3. So what's going to end up happening is I get 4 minus 8/3, and then when I substitute in 0, both of those turn into 0, minus this function when I substitute in 3 and 2. So what I end up with is 9 minus 9 minus 4 plus 8/3. So when I do a lot of stuff and like simplifying things, I get 4/3 minus negative 4/3, which is plus 4/3. So I get 8/3. So the actual area of this region is 8/3. So what that means is this part up here is 4/3, and it's canceled out by this 4/3 down here when we did the integral, so we got 0. So if I was just doing integrals by themselves, I would get negative 4/3 down here and positive 4/3 up there. They would cancel out to be 0. However, if we're talking about area is technically always positive, so I have to add those two and I get 8/3. Next, the mean value theorem for derivatives says there exists some point C on the closed interval a to b such that the derivatives, or the derivative, is equal to the slope of the secant line at some point. So basically what that's saying is I have the slope of the secant line from A to B, and that equals the slope of the tangent line somewhere, as long as I have a continuous and differentiable function. So that is something that we've learned before. Now, the mean value theorem for definite integrals. What that is if f is continuous on a to b, then at some point c in a comma b, the closed interval, we have f of c equals 1 over b minus a times the integral of f of x dx. This is essentially the average value of a function. So this is the average value of a function. So we do a little rearranging by multiplying by b minus a in this. And what we essentially have is we're finding the area of some rectangle, f of c times b minus a. So if we look at this, b minus a is going to be the distance on the x-axis or whatever of something. And then this f of c is the height. So we have base times height of this rectangle. Now, what that is going to do for us is that's going to tell us where exactly the area of this rectangle is exactly equal to the area under the curve for what we're trying to find. So we're basically turning the function into a rectangle that has the exact same area. We're like morphing and shaping it into a rectangle. F of c is the height at which this function's area is morphed into a rectangle over the exact same interval that we're talking about. Tip for the AP test: when asked to find the average value of a function, we want to do the mean value theorem for integrals. Find the average value of x squared on 0 to 3. At what point does this occur? So let's do the actual problem, and then we'll explore what it looks like on Desmos. So if we are trying to find the average value, that's the same thing as saying 1 over b minus a times the integral from a to b of f of x dx. We're trying to find the point that this occurs at eventually, after we find the average value. So what we're going to do here is we're going to replace b with 3, a with 0, and f of x with x squared. So 1 over 3 minus 0 times the integral from 0 to 3 of x squared dx. So this is 1/3 times 1/3 x cubed evaluated from 0 to 3. So if I take a look at this, I get 1/9 x cubed evaluated from 0 to 3. If I substitute in 3, I get 27 over 9, which is 3. If I substitute in 0, I get 0. So my average value of this function is 3. This is going to occur where x squared equals 3. So x should equal plus or minus the square root of 3. Since we're on the interval 0 to 3, it's going to be the positive version. So x is going to equal square root of 3 in this case. So let's take a look at what's actually happening. Remember, the mean value theorem for integrals is us taking this curve and the area underneath it and turning it into a rectangle that has the exact same area from 0 to 3, since we were doing it on the interval 0 to 3. So what I'm doing is I'm trying to move a value on the function and find a rectangle that has the exact same area as the whole function. And what ends up happening is when I get to about 1.73, 1.72, that's about what the square root of 3 is. What ends up happening is I get a rectangle that has the exact same area that the function had. Now, if I go past this, my area of the rectangle is too big, and so on and so forth. So what I'm trying to do is I'm trying to find this spot where I end up with the area of the rectangle being exactly equal to the area that's under the curve. Finally, find the average value of f of x equals 3x squared minus 2x on 1 to 4 and the points where it occurs. So I do 1 over b minus a times the integral from a to b of f of x dx. I find an antiderivative of 3x squared minus 2x, which is x cubed minus x squared. 1/3 times that when I substitute in 4 minus that when I substitute in 1, I get 1/3 times 64 minus 16 minus 1 time 1 minus 1. So I get 48 minus 0, which is 48. So 1/3 times 48 gives me 16. 16 is the average value. Finally, I want to find where the average value occurs, and that occurs at 8/3 because I take 3x squared minus 2x and set it equal to the y value that is this average. I'm going to cut that down to just being from 1 to 4. And what I want to do then is find some rectangle that has the exact same area under it as um, what would happen if I go from 1 to 4. So notice this actually extends all the way up to here. So I want to find the red area to be equal to the black area. And so what I do is I end up kind of scrolling along and I find out that it occurs at 8/3, which is exactly what I thought would happen. So 8/3 comma 16 is where that happens on my graph. So the area of the shaded regions, I did this in 2 different ways for most of these problems. So the first one, we have this area. That really wasn't a very good color to choose. So we have this area, which is going to be negative. So I'm going to have a negative sign here in order to cancel that out and basically make it positive for me. And then we're going to add it to this integral. So I have negative integral from 0 to 1 plus positive integral from 1 to 2. So I calculate it. An antiderivative of x squared minus 1 is 1/3 x cubed minus x. We're going to use that for all of the problems. I do a lot of substitution with 0 and 1, and then 1 and 2, simplify things, and I get 2. For the second problem, I have this shaded region, which is basically the rectangle that has length or height of 3 and length or width of 1. So I want that rectangle and I want to subtract the area underneath. So that's going to be what I show in black. Or I could do the function 3 minus x squared minus 1. So I have 2 different ways to do this. If I take the integral from 1 to 2 of the function 3 minus x squared minus 1, that simplifies to 4 minus x squared. I take the antiderivative of that, which is 4x minus 1/3 x cubed. Do that from 1 to 2. I do a little substitution, I solve, and I get 5/3. If I did it the geometric way, I have that rectangle with area 3, and then I subtract what I already found earlier, which was that the integral of 1 to 2 of x squared minus 1, that's 4/3. So I already found that earlier. So I do 3 minus 4/3, and I get the exact same answer, 5/3. Finally, the problem on the right, there are a couple different ways I can do this. The algebraic way, or the completely calculus way, would be taking the function 3 minus x squared minus 1 and just integrating that from 0 to 2. So if I do that, I will end up with 16/3. So here's the work for that. I integrate 4 minus x squared. I sub in 2. When I sub in 0, that ends up being 0 anyway. So it's 8 minus 8/3, which is 16/3. Or what I could do is I could treat this like it's geometric in nature. And if I treat it like it's geometric in nature, what I have is I have this down here, which I already calculated as negative integral from 0 to 1 of x squared minus 1, and I found that this was 2/3. And then I'm going to add on top of that a rectangle 3. So it's 3 plus this area, which is the same thing as 3 minus this integral. So keep that in mind. 3 minus this integral. Then I also have over here the rectangle 3, and then I'm going to subtract this red shaded area, which over here we found to be the integral from 1 to 2 of x squared minus 1. So I did that in black. So I have 3 minus that integral. And then I added 3 minus the second integral. Since I already calculated this, that was negative 2/3. So this becomes 3 plus 2/3. And then over here, I already calculated this in the second part to be 5/3. So 3 plus 2/3 is 11/3 plus 5/3 gives me 16/3, which was the same answer I had earlier. So I could do this either with geometry or like calculus and geometry together, or I can do it with just calculus.